Good morning, everyone, and welcome to the P and Applied Mathematics seminar. It's a pleasure for me to open session 41 of this seminar. Today we have two excellent speakers, Manuel del Pino and Kevin Levac. Introducing Manuel del Pino, we have to Professor Mauricio Sepúlveda. Thank you, Mauricio. You can start.
Okay. Thank you to Manuel del, thank you, Juan Limaco, for this introduction. And thank you, Manuel del Pino, for to speak in this seminar. Manuel del Pino, I know, is a great mathematician. I know in the time of when we are students in Universidad de Chile, a long time ago, and we are friends. Manuel del Pino is an important mathematician. He has the National Prize of Science, he obtained in 2013, and he worked in, he have his PhD in Universidad de Minnesota, and he worked in different universities in Princeton, Chicago, and Universidad de Chile. And now he's in the University of Bath in the Kingdom, the United Kingdom. And okay, it's a pleasure for me to present Manuel del Pino. His talk is about dynamic of concentrate vorticities in 2D and 3D Euler flows. Okay.
Okay, so thank you very much, Mauricio, for the very nice introduction. Well, it's actually very special to be introduced by a true friend, an old friend. Say with Mauricio, he didn't say it, but we probably know each other close to 40 years, right? Hmm?
Mm-hmm. Yeah.
Yeah, that's a very long time. Okay, so thank you very much also to Juan and to the organizers of this seminar. It's truly international seminar, for what I see. Okay, I would like to tell you what we have been working on, which corresponds to solutions of the standard Euler equations for an incompressible fluid with highly concentrated vorticities. So the Euler equations, or the Euler system, in 2 dimensions for an incompressible fluid in ideal conditions can be represented by this relatively simple equation, nonlinear equation, which is the transport equation for this quantity omega, but where the transport term itself is a non-local operator in omega. Say we set it to be the inverse Laplacian of omega, and then what we consider is this initial value problem, and we are interested in solutions for which omega has an important concentration in terms of mass near a finite number of points. Okay, so the inverse Laplacian, I simply mean the Newtonian potential, nothing else. The velocity field of the fluid in the plane, okay, is idealized as the gradient, as the perpendicular of the gradient of this function psi, which is called the stream function of the fluid. And it is explicitly given by this formula, of course. This is just the gradient of the Newtonian potential, and then with the perpendicular taken. Okay. The vorticity, the quantity omega, which is a scalar, corresponds to the curl of the velocity field, and it is explicitly given by this quantity, so it can be identified with a scalar. Okay, so for this initial value problem, a lot is known. In fact, this equation is relatively well behaved when you compare it with the 3-dimensional case, which is, as perhaps everybody knows, considerably harder, considerably more delicate. In particular, you have quite a few results concerning well-posedness of the problem in different spaces. And let me mention, for instance, that the problem is well posed in L infinity, the inverticity form, the equation in vorticity form. So if you consider an initial condition in L infinity, the solution is well defined and lives for at all times, yeah, in the right weak sense. And it's at all times it is bounded, it is in L infinity. And in particular, it doesn't develop singularities. In reality, if the initial condition is smooth, regular, the omega does not develop singularities in finite time. It can, in a certain sense, if you go with time going to infinity, okay? But it's not the case otherwise. Okay, this is very characteristic of this Euler incompressible equation in 2 dimensions. Del infinity well-posedness was already found by Judovich in 1963. This is a classical result for this problem. Let me mention one simple observation, but very interesting, is that in reality, whenever you have a solution, I mean a steady solution, time-independent solution, of this elliptic problem of a semi-linear elliptic equation of this form, minus Laplace of psi equal some function of psi, yeah? Meaning f of psi at x. Then such a solution of this problem, inherits a steady state for the Euler system. Why? This is not hard to see. What happens is that if you take the gradient of this guy, of f of psi, then you get something that goes along the gradient of psi, and then the dot product here is 0. And well, it is time independent, so this is 0 as well. So this is why this is it would correspond to a steady state. Let me mention a particularly nice example, which is called sometimes the Kaufman-Scully vortex, given by this particular function, this particular radial function, yeah, which is a solution, which corresponds to a solution of this elliptic equation, another classical object, which is called the Liouville equation, and for which its entire solutions are all known. They all have finite mass. And interestingly enough, that finite mass is always say pi. In reality, all solutions of this equation with finite mass can be represented as a translation and scaling of this object, which is what we call the Kaufman-Scully vortex. In reality, let me tell you that if you take any positive radial function as any that will inherit through this formula a steady state. Let me tell you what I would like to describe. I would like to describe the evolution of solutions of the vorticity equation with the vorticities concentrated around a finite number of points. So what I would like to consider is a solution which looks approximately of like this, a linear combination of Dirac deltas, a superposition of Dirac masses. Now you might say, well, why? You would expect, for instance, that such an object could be a solution in some weak sense. Well, it is not so crazy in the sense that the equation, this transport equation, preserves mass. Okay, you can algebraically see it right away. So if you are near a spot which is compactly supported, you will see the same mass all the time. So if this is the Dirac delta with mass 1, well, this number 8 pi kj is independent of time, should be the same for all times. Okay, and if the supports are disjoint, well, you also expect that the sum of those will be a solution. Anyway, if for a solution of this form, the string function will obviously have this corresponding form. I mean, this is the fundamental solution for Laplace and normalized because we have this number 8 pi here. Yeah? Okay, I will consider this particular situation. So what does this represent? Well, this might represent a configuration of of course, extremely simplified of a situation, of a planar situation, like the one picture here that I suppose is not a real thing. Okay, you have 3 typhoons aligned, one after the other. And so this is a situation of a solution of the Euler equation, say the fluid is the atmosphere, for which the vorticity is very high around this finite number of points, which are evolving. This would represent the centers, psi j of t. Of course, this is a very rough approximation, and even for atmospheric model, the Euler equation is not the best. Well, the analysis of solutions with highly concentrated vorticities is a very old subject. These are solutions or phenomena that attracted the mathematicians since the very origins of the study of fluids. In particular, there was a quite systematic analysis of this type of objects due to Helmholtz in the mid-19th century, and also by Kirchhoff, and then and by other people. So in particular, these latter people, Rose, Lagalli, and Cicilline, understood formally what was going on for the configuration of vorticity of this form. Of course, this is extremely singular object, and this guy cannot represent a true solution because solutions are smooth. If you are in the eye of the hurricane, say like here, you see velocity 0, yeah, right? So you don't see a singularity. You see a truly smoothing effect. So the delta is an idealization, yeah, with infinite mass at a single point. However, it's not really physically plausible if you want to consider fine scale. Okay. Then, in this scenario, right? Say if we consider this singular guy, then the corresponding string function is going to be the inverse Laplacian applied to this guy, which is a linear combination of fundamental solutions with poles at the centers. So it should be this. What I would like to show you is that it is plausible to have that an object like this pair, is a solution of the equation of the Euler system in some formal sense, provided that the centers psi j satisfy a certain system of differential equations. So formally we compute, right here, let me show you very quickly this computation. If you compute this guy, which is, I mean, we should be 0, right? If this was a solution. Well, I make the computation again formally. So I have to differentiate direct deltas, which is rather unpleasant, okay? But I get these singular objects here. And here I get something even worse because I have a double summation and with these products. And these functions are singular. So you see that something horrible will happen when I is equal to j, because this is a very singular object multiplied by this singular distribution, the gradient of the direct delta. Well, that looks bad, but luckily, at least in a formal sense, I can say that gamma of x, the fundamental solution, and delta of x, the direct delta, are radial functions. Since they are radial functions, this is what you get, right? I mean, the gradient perp of gamma times the gradient of delta for any pair of radial functions around psi j, that's going to be 0. Yeah. Therefore, this pair omega s psi s will be a solution of the vorticity system if and only if all these coefficients here turn out to be 0. 0 where x equal to psi j for xj. Remember that this distribution is supported only at the point psi j. So what I need is that these coefficients be 0 exactly at x equals psi j. And that is equivalent, again, we are lucky, and we get that that our pair psi s omega s is going to be a solution quotes, yeah, because these are not smooth functions, if and only if this system of differential equations, this is a Hamiltonian system, is satisfied. Okay, this is called the Kirchhoff-Rosse system. And well, I write it here again. Okay, now the question that I would like to attack is the following. These guys are formal, what I just mentioned. So the question is, are there true solutions of smooth solutions of the Euler system whose dynamics is truly represented by this system of differential equations? So, in other words, are there true solutions, smooth, of the Euler system with vorticities highly concentrated around a finite number of points, where those points evolve by a dynamics approximately given by this? This is the question that I would like to answer to begin with. So this was our original motivation to study this. Now, what I will do is to show you how I would like to regularize. This is not arbitrary. I will tell you in a moment what I mean. Okay, let me do a regularization. I mean, here are my singular objects, okay? What I would like to do is a regularization of these Dirac deltas using scalings and translations of the Kaufman-Scully vortices. That, remember, the Kaufman-Scully vortices are steady states. So what I will do is to replace the Dirac delta by this omega 0, by this W0, centered at x minus ij divided by epsilon, and naturally multiplied by 1 over epsilon squared, because this is the scaling that preserves mass. So the mass of these objects is the same for each epsilon. And imagine what happens. The mass of this guy is in reality 8 pi. This is the reason why I was using this factor 8 pi, this artificial factor 8 pi before. Okay, what I am doing then is a regularization of the Dirac delta. And in what way this fundamental solution is being regularized? Very simple. This power 4 becomes 2 and 2 here, and the pole is desingularized by adding epsilon squared. So you get these nearly singular guys, however smooth, very concentrated. And what I would like to show is that there is a true solution with that approximate behavior. What we have is that, of course, by definition, yeah, because of the Kaufman-Scully vortex, the one defined by the Euler equation, I have this situation here. Yeah? And what I will get is that the omega 0 epsilon, this approximate solution, is going to converge as epsilon goes to 0 to a sum of Dirac deltas. This is clear, right? Because they are concentrated. This omega epsilon is I mean, each of these guys is approaching a Dirac delta. And I also have this additional information which corresponds to the density of the kinetic energy. This is the velocity field. Yeah. So the velocity field, the absolute value squared, say normalized by this factor log of epsilon, is going to converge weakly to this combination of Dirac delta centered at the points at the poles ij. So our main result for this problem is that for a given collisionless solution of this system, I have to consider solutions that don't have collisions. Otherwise, the regime is different. So these poles remain in a given time interval, separated. Okay, they don't collapse one onto each other. So I consider a solution of this problem. And then what we prove is that there is a solution of the system that differs little from this basic object size 0 epsilon W0 epsilon. So what we prove is the existence of a solution that looks truly like this, where I can express very accurately what these spikes are. Okay, so this is result that we published a couple of years ago with Juan Dávila, Mónica Musso, and Yunchen Wei. Okay, so what we consider is a collisionless solution in 0T. Then there exists a solution of this of the vorticity system with this form. Yeah. Where these are the approximations that I was mentioning before, and this phi and psi are remainders that satisfy the following. Look at what at the level of psi, what happens. This psi guy is extremely small. As a matter of fact, it's of size epsilon squared. So this, instead, this is almost singular. So this is really small. And what we have at the level of the vorticity, the control for the vorticity, is a little worse, okay? In fact, already the one of the gradient is worse. The gradient is of size epsilon. But the vorticity, which is a sort of second derivative of psi, yeah, it's the Laplacian of psi. The vorticity, in reality, we can control it by a fraction. We can do better than this, by the way, but at least for the purpose of this talk, I will just mention that what this phi is a fraction of the main term, a fraction given by a power epsilon to the sigma for any sigma less than 1. Okay, this is what we get. So in particular, what we have is the convergence, the distributional convergence of the solution, of the true solution, into the superposition of Dirac masses centered at this particular solution. And this and the velocity field satisfies the kinetic energy, satisfies this conversion as well. There was a previous result. Our result improves. I mean, we believe in a rather substantial way. A prior result by Marchioro and Pulvirenti, where a solution satisfying the first condition, a smooth solution satisfying the first condition, however, not the second, was found. The difference, the approach they use and the approach our use are completely different. And essentially, they cannot say much about what's going on near the vortices. So it's a sort of external problem what they have control of, okay, of what happens outside of the core. But at the core, they have essentially no information, no precise information. Okay. Let me tell you how we proceed in order to solve this. This is the ingredients of the construction in the construction are the improvement of the approximation first in powers of epsilon, and we do that by using a combination of resolution of elliptic equations and transport equations. Later, what we do is we set up the problem as a coupled system of inner problems near the singularities expressed in the scale of the bubbles near the singularities, and an outer problem which is more regular. And this coupling between the external and internal regimes is what gives rise to the true solution. Now, in order to solve for the true solution, we will need to adjust all parameters involved, in particular the centers, yeah, which we leave as parameters in a very precise way, so that certain solvability conditions are satisfied. And we will be able, only in that scenario, we will be able to solve the full system. So later on, what we do is we prove the presence of a priori estimates for these linearized problems, right? And we eventually solve using Leray-Schauder degree argument. Okay, concerning, just to give you a flavor of why such a thing can work, let me consider an approximation, our approximation of the solution using psi 0 epsilon. Psi 0 epsilon can be written in this form, where gamma 0 is this guy. Why do I like it written in this form? Because this is gamma 0 of y, and this is y. And y is the natural variable near the point. So I would like to even express the equation in terms of y, the space variable in terms of y, or in terms of this variable, in order to have a better feeling of what's going on. Okay, so what we want to solve is this equation. We know that, right? And what we do, expressing the equation in this variable y, is to look for a solution that looks like a perturbation of the psi 0 epsilon, and which I choose to have this particular form. kj times kappa j times psi, little psi, but which is a function of y, not directly of x, but depends on x through y. Okay, and omega will be taken as the specific bump, right? Expressed in terms of y. This is the approximation that we are using, plus another remainder that I choose to have this one. So in terms of the y variable, the expression for the operator after we multiply by epsilon to power 4 is this equation. It's an equation where phi t, the derivative of phi t, comes multiplied by epsilon squared. And then we have all these factors. All these factors appear. What we have then is that psi 0 epsilon can be written as kappa j gamma 0 of y plus some remainder phi of x. And this phi of x is nothing but this, this function. Yeah. But on the other hand, what we know is that psi j dot at main order is equal to this gradient perp of phi. Okay. The equation for psi j can be written in this form. And therefore, we get the validity of this result that, I mean, it tells me that this plus this can be expanded in this form, where this R is an object that carries epsilon squared. So in summary, the error operator becomes epsilon square phi t plus kappa j times this gradient of gamma 0 plus this R, okay? And this R is quadratic, is of order epsilon squared y squared. Well, and times this guy, yeah? So what do we do now? What we do is we linearize this problem, yeah? And so this R, remember, is like epsilon squared y squared. And now let me write f of u equals e to the u. Remember that the gamma 0 satisfies the Euler equation. So W0 is f of gamma 0. Yeah. And we find that this is epsilon to power epsilon to the 4th times e. And that gives me this linearized form for the equation. Okay, so look at what happens. I have this term, the derivative in time, and I have this elliptic operator. This elliptic operator maybe looks familiar what this is. This is nothing but the linearization of the Euler equation around this solution gamma 0, but this comes multiplied by this factor, and this factor is very terrible because that makes this operator extremely degenerate as an elliptic operator. Why? Because if you take any radial function here, then the gradient is going to be the gradient of a radial function that multiplied by this is 0. So remember that all radial solutions are steady state. So this is not surprising. And then the error becomes this guy. So what we do? What we do is to solve for say the 0 order error term is this guy, yeah. The 0 order, I mean, when phi is 0, phi and psi are 0. So the first error is epsilon squared over y to power 4, but this is not enough for us. In reality, we need more. We obtain a reduction in the error by solving this elliptic equation. Because I simply pick up this term and then I add this one, right? And so if I am able to solve this elliptic equation, then I get an improvement of the error. In fact, this is what we get. And it turns out that if I reproduce this with this procedure, in fact, the error that started being epsilon squared becomes epsilon to power 4. But epsilon to power 4 is unfortunately not enough. The reason is that this term is quadratic, and eventually we will want to solve an equation that carries epsilon squared phi t. So if you solve it by integration in t, or at least in along some component, then you lose 2 epsilon. So epsilon to power 4 is not enough. However, we manage using a combination with a transport equation, which is the main term here. Yeah. Then we get an error which is epsilon to power 5 divided by rho cube And this turns out to be good for us. Okay, this turns out to be good enough for us to solve the full problem. A basic ingredient to get a priori estimates is the following: is that this linear, for the linear equation, for the linear equation, we are going to get, say, ignoring this quadratic term. In reality, this is the way to say it. We find that for perturbations phi, which are mass zero and center of mass zero in a large ball, we get something like this. So you lose 2 epsilons. This is due to the epsilon square here. And you, in addition, lose a log of epsilon. Yeah. And this is the type of estimate that we get. And this estimate allows us to use a fixed point scheme to solve with AE equal this guy. Sorry, this guy here is actually 4. Okay? So you see the del 2 norm loses epsilon squared. Okay. Now, let me tell you some more recent work, which is actually more suitable as an atmospheric model. The atmospheric model actually is a very similar equation to Euler. However, Euler is not the most appropriate thing. It's more appropriate to use powers of fractional Laplacian rather than of inverse fractional Laplacian rather than Laplacian itself. And these these problems are called the surface quasi-geostrophic equation. The true or the basic surface quasi-geostrophic equation corresponds to the case S equal to 1/2. Okay. However, this equation makes perfect sense for other values of S, even at the level of model. That's perfectly okay. And what I consider is the case when S is bigger than 1/2 and less than 1. That is sometimes called, actually, you ask the particle generalized here, generalized surface quasi-geostrophic equation. Okay, so the inverse fractional Laplacian is this guy. This is the fundamental solution for the inverse, for the fractional Laplacian. And this is the system. So it looks very much like the other, except that the other carried log, convolution with log. On the other hand, even though the difference is, in principle, looks not so big, but it turns out that this problem for values less than 1 is substantially harder if we want to construct a solution with the same features, with highly concentrated vortices. It's a more difficult problem. And this is something we have obtained with my former postdoc, Antonio Fernandez. And we have been able to arrive to the following result: that if we have a solution, collisionless solution of this n-body problem in a fixed interval of time, then we can find a true solution of the problem where the corresponding quantity for vorticity is going to have this form where this function u0 is now this power 1 plus s, which are extremals for the Sobolev inequality in the fractional case, in R2. So just one thing, and this is not minor, restriction. We have been able to do this only for values of S which are bigger than this number. 0. Well, the number is approximately this, but say we have the result for S bigger than 0.937. So if you want to go below that, our method kind of breaks apart. It is a complicated problem. You need to deal with approximations, with improvement of the approximations of higher order to begin with, and then the iterations to get a priori estimates are much more delicate. I mean, this is a little bit the bottom line, and if you take it low enough, you simply cannot do it. At least not in the way we have been dealing with the problem. Let me tell you that looks cosmetic. However, the difference between the surface quasi-geostrophic equation and the other is not minor. Let me mention that a special case that had been worked before was worked by my joint work with collaborators, Ao, Juan Davila, Musso, and Wei, this was recently published, and which is a traveling wave solution for a vortex pair, which is a special solution for this thing. However, this is a reduction to an elliptic problem, so it's a much easier problem. But just to mention that there was some results before, and some partial results in the lines that we have, the one that I am stating, are by these authors. Let me mention one thing. Is that a big difference with the standard Euler is that there is no theory for well-posedness, no good theory for well-posedness in large times. Yeah, unlike the Euler equation, there's no such a theory for the surface quasi-geostrophic. So if you really want to construct the solution, you have to do it by hand. Yeah, it's that is a true difficulty in the construction. Okay, so if you may wonder what happens in our constructions if we take long times, this is a natural problem. This is a natural question, and this is something we have been working on with Juan, Monica, and our postdoc Swish Padmeshwar. And we have considered the following situation: simple situation, which is a special criticality situation for vortices, which is two vortex pairs, one traveling to the right and one traveling to the left. There is an interaction between these two blocks, but look at what happens. We actually have exact solution with this behavior. So we have one traveling to the right, one traveling to the left. So the error created, since these guys are exact solutions, is small. It's small in the sense that it is decaying in time if these directions are taken the same as symmetric. So this is the bottom line. That now that what we want to find is a solution of this form for some basic profile U here, and where this quantity little of 1 is in reality going to 0 as time goes to infinity. Yeah? We have been able to find a solution with these characteristics. We are in the process of writing the result. Now, let me say something about the three-dimensional case, because of course these vortex situations, are actually more realistic in 3D. In 3D, what you would see is, I don't know, tornadoes, right? Like a sequence of tornadoes, like this picture. Another, I suppose, it's another situation, not real. But you can imagine what happens. I mean, these curves are moving, right? Are evolving, not just the basis, but in reality, in the rest of the body of this thing, they are going to move. This is a true picture. It's the volcano Stromboli in Italy, and this it's just a smoke ring, right? And the smoke rings are objects that have been known in these fluid equations for a long time as well, and they are related. I mean, the motion of these guys that we call vortex filaments, that are simply situations, vortices in 2D are replaced by these vortex filaments that are actually solutions with highly concentrated vorticities near curves now. Yeah. In this case, the curve is an S1 traveling. And in this case, well, what you see. Now, the problem of even at the formal level, finding what is the motion, the law of motion of such objects is very old, and it has not been at all understood over the years. In fact, the law was discovered more than a century ago by Darrios, who was a student of Levi-Civita. This discovery comes from 1906, and he discovered this law of motion, which is now known, as the vortex filament conjecture. So, because this is a formal law, yeah. Okay, so now let me explain you what do we mean by that vortex filament conjecture. In R3, the Euler system in vorticity form has a more complicated form. So in reality, this term is quite similar, except that omega now is vector valued. Use the velocity field, which is given by the curl of a string function. Now the string function is given by this, by the way. But you have this term here, which is called the vortex stretching, and vortex stretching creates all type of trouble, okay? Even as the well-posedness of the Euler equation in R3 for smooth solutions is unknown until today. In fact, people believe more likely that there is existence of singularities in finite time, but this is maybe not so close to be truly proven. Okay? So, okay, let me tell you what this vortex filament conjecture is. If we have a time-evolving curve gamma of t parameterized in this form, in the vortex filament dynamics, say that I want to find a solution, omega epsilon, vector value, but that now behaves like a Dirac delta, but along the curve. So it's really concentrated, its mass density, near the curve gamma of t, and the direction of this vector value guide is the tangent vector to the curve. So what we should see is something like this, where this delta is the Dirac delta along the curve, yeah, as a measure. So this is what we would like to find as epsilon goes to 0. Now, what Darius discovered was that actually in order to see something, some nice law of motion, you actually have to scale in the time. You don't see it directly, but you have to make a scaling in time of this type. And say the gamma parametrization, then eventually, as a function of tau, is going to satisfy as epsilon, as this concentration goes to 0, the concentration parameter for the filament, which is the width of a neighborhood like this. Then as epsilon goes to 0, you find this. You find this law, which is called the binormal flow of curves. Yeah, this is the guy we are talking about. So the formal the vortex filament conjecture states the existence of a solution, so that if you scale time in this way, then you approach this there exists solution with this characteristic where gamma of tau is a given solution of the binormal flow defined in a fixed interval. Now, it is natural to get such a thing in light of what I showed you before, right? Is to look for a solution of this form, where the Dirac delta is replaced by this, where z is simply the distance to the curve from a point x. And it turns out that this statement for things like this is only known for special curves associated to traveling wave solutions. Yeah, in fact, this is known for vortex rings, yeah, like this, and for helices, by rotating helices. And this is the only cases in which this is known. In fact, we have been able to prove it in the case of a helix. In that case, the problem of a rotating helix reduces to an elliptic equation, which we have been able to solve by linearizing the Liouville profiles like this. So this is again a result with Juan, Monica, and Cheng, which is comparing calculus of variations. So this is the classical solution of the binormal flow. So the other situation is the case of the vortexes. If we use in the axis symmetric Euler with not swirling, the problem luckily reduces to the analysis of a scalar function. And this is the equation now, which is now for a scalar function. And what we have now is the presence of solutions which are vortex rings traveling with high velocity, log epsilon, in the vertical direction. So now another conjecture that has been open for a long time concerns the interaction of two vortex rings or of several vortex rings. Yeah. So what happens is there is a sort of periodic motion, in which the vortex rings cross each other by modifying their radii and their velocity, more or less like in this picture. This is a phenomenon already observed by Helmholtz, surprisingly, but not with mathematically precise form. It has been open since then, and you can see a lot of, in fact, nice experiments and so on in the literature, in YouTube even. However, not rigorous proofs, and we have been able to find in a scenario like this with two rings, a situation like the one I am describing here, yeah, which is the one described by Helmholtz. This had been done before in the Gross-Kitaevsky equation by Gerard and Smets, but Euler is much harder. They were motivated by Euler, but they couldn't do it. Our main result is that we can actually find for this equation, which is the good scaling for our equation, the existence of a solution that is approximately concentrated like this. This corresponds to the leapfrogging phenomenon with a specific scalings. In reality, we do that for special solutions of this type of embodied problem. Okay, if you want to do it within rings. And this is it. This is an interesting conjecture by Helmholtz that these methods appear to be adequate to find a proof. So thank you very much for your attention.
Thank you very much, Manuel, for your excellent presentation.
Thank you.
There is some question.
Está abierto el audio.
Juan, ¿cómo se activa el audio para todos? ¿O para...?
¿Dónde está security, yo creo?
Security.
Unmute themselves.
Sí, permitir. Reactivar, creo que está. Creo que está permitido. Está abierto audio. Okay. Manuel, your solution are all the times are classical, no?
Yes.
Classical solution, and the convergence to the Dirac is in the distribution sense, and your errors when you make some estimate, the estimate in which space you consider the
just very simple spaces, just very standard spaces. The two weighted L2 spaces, and then infinity, directly infinity things. We even need C1 estimates at some point, which are hard to get for Euler, know better than me.
Okay.
But yes, that's the situation.
And the other question is in the theorem with Fernando. You have is between 1 and 0.9. This number.
The reason why this number appears is technical. It's because we need to make a certain iterative procedure to get the a priori estimate, and this the iterative procedure at some point fails unless S is close to 1. So it is a technical thing, but we haven't seen so far a way to improve that. But anyway, it's not so surprising that we get values like that, because if you see the results in the literature for this thing, I mean, even at the level of finding vortex patches, for instance, there are results of existence with some regularity, but the regularity is only obtained if you have S bigger than 0.887, you know, or things like that. You know, it's not so surprising that you see this type of constraints.
Okay. Other questions? No? Then we thanks Manuel for his presentation.
No, thank you very much for the invitation. No, it's an honor speaking in this seminar. Thank you.
Thank you, Mauricio, and thank you a lot, Professor Manuel del Pino, for your amazing talk.